Okay, so electric force 1 by 4 pi epsilon naught q1 q2 upon r square. The magnitude is, and q1 q2 is the charge, and the distance between them is, let's say, r. So this is electric force. What else we have discussed? Field.
Field.
Field is, let's say we denote it with E vector. If we want to write the field, it's a magnitude, then 1 by 4 pi epsilon naught, only 1 q by r square. So let's say a charge is there, plus charge, the field will be in the surrounding of this charge, and for plus charge, the field lines are away from the charge, and for minus charge, the field lines are toward the charge. This is very important concept. When you are solving, you will solve the questions. This concept we have to use. That minus charge, the field lines will be, the field vector will be towards the charge. For plus charge, the field lines will be away from the charge. The field lines will be away from the charge. What else we have discussed so far in this chapter? We have discussed flux. What is flux? Flux we have, the flux is E dot dA, E dot delta A. A is the area, E is the electric field, and the dot product, you know, E dA magnitude cos theta. Dot product comes with the, that will be cos theta. Okay. But try to understand the theta, the angle that I have told you. What is theta? Theta is the vector, the angle between, suppose this is the, these are the charges, they are creating a electric field E. So theta is the area vector. Area vector is perpendicular to the area. So theta is this angle between E and area vector. So if we will hold the object parallelly, this n cap direction will change. So theta is this angle. So if they are same direction, so theta will be 0. If we'll rotate the, if we'll hold the your object with certain angle to this E, then theta will change. Okay, so this is the theta. So we have discussed flux. We have discussed also Gauss law. We have discussed Gauss law in this chapter. So what is Gauss law?
Sir.
What is Gauss law? Gauss law, we have discussed that. Gauss also told about flux, but he told about that Q inside by epsilon naught. This is your flux. We get the definition of flux, that Q inside or Q enclosed.
Charge inside by the epsilon naught.
And suppose this is a box, and inside this box some charges are there. Some charges, you will add all the charges which are inside the box, that will be Q inside, divided by epsilon naught, you will get the flux linked with this whole box. You will get the flux linked with the whole box. What is the meaning of flux? Flux is the number of field or field lines interacting with a particular area or passing through a particular area, that is just flux, right? Number of field, or means the field amount. Okay, the number of field lines or the field passing through the area, particular area is your flux. Okay, right? So these are the things we have discussed. Then we have discussed about the application of Gauss law. Two applications, at least in the last class, we have discussed. Applications of Gauss law. We have used the Gauss law to find out the electric field in different situations. Like two cases we have discussed in the last class. that is application of Gauss law. Application of Gauss law. So application of Gauss law is the application of Gauss law. We have used two cases. One case we have used to find out the electric field. Find out the electric field electric field electric field electric field of a uniformly charged electric field of a uniformly charged long wire so wire case we have discussed. Then second case we have discussed that electric field. Whenever I'm sending these slides, I'll send and you note it down after the class. The derivation.
Yes, sir. Yes, sir.
Because if you will not practice, you will not able to derive. And these questions comes in the board exam.
Yes, sir.
This time during the evaluation, I've found that the students are unable to derive properly. Suppose few steps they have done, then they couldn't complete the derivation, right? So this is because the lack of practice only.
Yes,
so
sir.
Electric field of a uniformly charged plane sheet. Uniformly charged plane sheet. Okay. Plane sheet. So two cases we have discussed in the last class. Sheet and wire. Sheet and wire. Do you remember the formula for sheet and wire?
No, sir.
Where what we got? This is a single wire. Uniformly charged means charge is distributed over this wire. So there will be electric field in both directions. You have done this derivation, right?
Yes, sir.
Class you write it again. Else you will not able to remember. So let us choose a cylindrical surface which will enclose this charge. Why we are taking so? Because we want to use the Gauss law here. Let's say this is the cylinder which will enclose the charges of length L up to length L. So if lambda is the charge density, that means number of charge per unit length. So for L length, how many charges will be there? That means Q inside will be lambda
You have to
into L.
multiply it with, yeah, lambda into L.
So if we'll use Gauss law, here, then your flux equal to flux with the cylindrical surface equal to Q inside by epsilon naught, and Q inside is what? Lambda into L by epsilon naught. This is, let's say, equation 1. This
Yes,
is your
sir.
equation number 1. Now, also we know that the definition of the flux, from the definition of the flux, we know that flux equal to E dA. So this is your E dA. You see, E direction is this one, area direction is also same and get. So for this curved surface, E vector and A vector are same. So cos 0 is 1. So only E dA will be there. Clear?
Yes, sir.
And dA here is what? Area of this cylinder, curved surface area. The curved surface area of the cylinder is what?
2 pi RH.
Pi RH. Here
Pi
L
RL. Yeah.
pi RL. So it will be E 2 pi RL. Okay. E 2 pi RL. So this is also flux. Let's say this is equation number 2. Now from 1 and 2, what you can write? From equation 1 and equation 2, what you can write? Both sides, both left side are equal. So you can write right side, that is E 2 pi RL equal to lambda L by epsilon naught. LL get cancelled. What is our aim? Our aim is to find out the electric field, which is equal to E equal to, just cross multiply that lambda by 2 pi epsilon naught R. So this is the field you are getting for. This is the field you are getting for the uniformly charged wire at a distance R from the wire. So what is the electric field? So in vector form also you can write. In vector form, this is the magnitude 1. So vector form you will write that it will be along the direction of n cap, area vector. So you can write that E vector, because electric field is a vector. So lambda by 2 pi epsilon naught R n cap. This is the electric field for the plane, for the charge wire. Charge wire.
Yes, sir.
Okay.
Hmm.
So for plane sheet also we have discussed in the last class.
Yeah.
Field for the plane sheet. Okay. So plane sheet, if you will see, so this derivation you practice. So for plane sheet, let's say this is a plane sheet and it is charged. Charges are kept over it. So it is charged now. So it will create some electric field.
Hmm.
There will be field to the both sides. These are the electric field due to the charge. Now let us cut a cuboidal Okay, cuboidal surface which will enclose some charge q in. Okay, so why we are cutting it? We are cutting due to we are interested to use the Gauss law. So we are cutting
Yes.
a cuboidal surface. We are cutting a cuboidal surface this surface is enclosing it as it is cutting the sheet so that it will enclose some area, let's say delta A. It will enclose some area delta A. Okay. Enclose some area delta A. So
Okay.
here as it is a surface, so it is we will not use lambda here, we will use another symbol sigma. Okay, sigma is the number of charge per unit area. So for this small area delta A, what will be the charges inside and number of charge per unit area multiplied by area? This will give you charge inside. Okay, so you can use Gauss law. You can use Gauss law. So Gauss law is what? Inside by epsilon naught. Q inside
Hello.
is sigma by, yes. Can you hear me?
Yes, sir.
So your Q inside is sigma delta A here. Okay, Q inside is sigma delta A. So sigma delta A by epsilon naught is the first equation. Second equation, this is the flux. This is from Gauss law. This is the flux equal to this. Now also we know that flux equal to what? EDA. EDA. So that is E dA cos theta. Okay. EDA cos theta. Now EDA cos theta. Now E electric field is in this direction and area vector also for this side it is also n cap also this direction. So cos 0 will be 1. So it will be E into del A. Now look at the left side. Left side also. Look at the left side. Left side also. Left side also. What will be there? Now let us suppose this is flux at right side. Flux at left side is what? This is also EDA. E is this direction. Electric field to the left.
Yes, sir.
Area vector is to the left. So both are same direction. That means cos theta will be there. So this is also EDA. Now what about this upper, lower, side faces? Now for upper faces, the area vector NKP is upward, electric field is left. So angle is 90 degree, cos 90 is 0. So that's why 1, 2, 3, 4. Cuboid has 6 faces, right? The cuboid has 6 faces. So out of these 6 faces, only left and right face has the flux, this one. And other 4 faces, phi 1, phi 2, phi 3, phi 4, these are 0. flux 0. Why? Because you can write E dA cos 90. Cos 90 is 0. So this is E dA. But this is 0. So all the four faces 0. So total flux with this surface will be what? A total flux will be sum of all the flux. The
Yes,
sum of
sir.
the flux means only this one, phi right and phi left. That means EDA plus EDA plus EDA. That means 2 times of EDA. This is the total flux. Okay. And also from Gauss law, what is the total flux? This one, equation 1. This is equation 2. So from equation 1 and 2, left side equal, same procedure will follow. So from 1 and 2, left side equal, so you can write 2E delta A equal to sigma delta A by epsilon naught. Delta A cancelled out. So what will be there? We are interested to find E. Okay. So E equal to, this 2 will be divided here. Sigma by 2 epsilon naught.
Yes,
Sigma
sir.
by 2 epsilon naught. So this is the electric field. This is the electric field. This is the electric field, sigma by 2 epsilon naught. And this is the magnitude. This is the magnitude of electric field. So if you want to write the vector form also, sigma by 2 epsilon naught, and it will be in one direction, n cap, area vector direction. So this is the E in vector form. So the electric field in the electric field, it is sigma by 2 epsilon naught, remember, for a plane sheet, uniformly charged plane sheet. Electric field for a uniformly charged plane sheet. Okay. So this much we have done in the last class. So you practice again. Now we'll apply the Gauss law again to find out the electric field for a, or electric field of a uniformly charged cell. Okay, cell means a spherical cell, basically, like a football, you can say, imagine. So spherical cell, electric field of a uniformly charged spherical cell, electric field of a uniformly charged spherical cell. So how will you find? Again, same procedure will follow. Let's say this is a spherical cell where charge is uniformly distributed. Okay, so electric field will be there in all directions. Okay, electric field will be there all directions. These are the E vector. Now we'll draw a Gaussian spherical surface, which is hypothetical one. It is also spherical in nature. which will enclose this one, enclose this sphere. Okay, the outside one is the hypothetical one. Now, what will be the flux linked with the outside one? Now, flux linked, this is for two cases we will discuss. This is first case, that is field outside the cell. This for the charged sphere, spherical cell, we will discuss two cases. First case is the field outside the cell, field outside the cell, and in the second case we will discuss field inside the cell. Okay, field outside the cell and field inside the cell. So two cases we will discuss. So field outside the cell. So field outside the cell means this one is the bigger one is a Gaussian sphere.
Yes, sir.
Having a radius, let's say capital R, and the small one is a radius, or the small one is having radius R. Let's say outside this one, the Gaussian sphere is at a radius R. As per the NCERT notation we are doing, you can represent all different sign also, like X also you can represent. So this is a Gaussian sphere. This one is the radius R, and the outside sphere is of radius small r. So what will be the field link? What will be the flux linked with the let's say area delta A? So this will be the area vector which will be outward, and the electric field vector is also outward. So that means angle between them is 0 degree. So we can write that again the same thing, that flux equal to EDA, flux equal to EDA, which is EDA cos theta, or cos 0 is 1. So we can write E magnitude, delta A magnitude only. So what is the delta A area here? The area we can write E magnitude, area is 4 pi small r square. The area of a sphere, area of a sphere is 4 pi r square. So this is the flux linked with this Gaussian sphere, the outside one. This is, let's say, equation 1. This is, let's say, equation 1. Now also we know from Gauss law. What do we know from Gauss law? That flux, from Gauss law also we know that, from Gauss law, what do we know? That flux equal to Q inside by epsilon naught. So Q inside is this one, the total charge. Now this is a sphere. So in the last derivation, we have used the symbol here. For seat we have used sigma, surface charge density. For the where we have used the lambda, that is the linear charge density, that is the number of charge per unit length, right? So now for sphere, it is a spherical one. So we'll use volume charge density rho. We'll use volume charge density. So volume charge density will be what? Rho. So rho is the number of charge per unit volume. So for this V volume, what will be the your charge? So we will write Q inside, flux equal to Q inside by epsilon naught, and Q inside is rho into the volume, that is 4 by 3 pi capital RQ. This will give you the charge, right? Volume into density will, that is number of charge per unit volume into this volume, will give you the charge inside. What are the charge? How many charges are there over this? By epsilon naught. This is the Gauss law. So this is your equation 2. Same procedure will follow. Okay. So procedure is from 1 and 2 left side is flux, same. From 2 flux is same. So we can write flux equal to from 1 and 2, flux is same. So we can write E from equation 1, E 4 E 4 pi smaller square is equal to what? Rho 4 by 3. Okay, here also we'll not write volume, only we'll write 4 pi r square. Why? Because charge is not inside, only in the surface. It's a football, let's say, the charge is only over the surface of the football. So we'll not take
Yes,
volume,
sir.
charge is not inside the sphere. Only it is distributed over the sphere. So we'll take 4 pi r square, capital R square. So it is
Hmm.
rho 4 pi capital R square by epsilon naught. So your E will be, we are interested to find the electric field at a distance outside the charge sphere. So your E will be rho 4 pi capital R square by 4 pi epsilon naught small r square. So this is your expression for electric field that is outside a point of the charge sphere or charge, you can say thin cell. Okay,
Hmm.
a football. So if we find out the electric field outside, so this is the expression and this is the magnitude one. So vector form, if you want to write, simply n cap will come, n cap will be the direction that will be perpendicular to the sphere. So if you want to write in the vector form, rho 4 pi r square, rho 4 pi r square divided by 4 pi r square n k. This is the electric field for the charge sphere and outside the charge sphere. This is the electric field for the charge sphere and outside the charge sphere. Now what about the inside the charge sphere? What about inside the charge sphere? On the case 2, this is first is field
Hmm.
outside. Field outside. Okay. Now case 2, field inside. So field inside case will be the simple one.
Hmm.
Field inside. The second case of the spherical charge spherical cell, that is field inside. Field inside. So what is the field inside? Field inside is, let's say this is a charge sphere. So charges are distributed over this sphere. Charges are distributed over this sphere. Now we are interested to find out the electric field inside at a distance, let's say r from the center, any point inside the sphere. Last case we have found out for outside the sphere. This one is for inside the sphere.
Hmm. Yes, sir.
Inside the sphere. Okay. So for inside the sphere, again the same procedure you will follow. That
Hmm.
for inside the sphere, your flux from Gauss law, from Gauss law, flux is what? Flux equal to your Q inside by epsilon naught. Now
Hmm.
you see, if this is the Gaussian surface, right, which is inside the sphere, let's say inside the football, and the charges are charges are in the surrounding of the um, football. So inside the sphere there is no charge. That means inside this Gaussian surface there is no charge. So Q inside will be 0.
0.
No flux will be linked according to Gauss law. No flux will link with the surface which is inside the spherical cell. Okay, inside the cell. Now from
Yes, sir.
so this is equation 1. We need 2 equation now. So this is from Gauss law. Now from general definition of flux, we also know that flux equal to EDA.
Hmm.
Here the surface area is E 4 pi r square. This is your equation number 2. So from 1 and 2, same procedure will follow. From 1 and 2, okay. From 1 and 2, what we can write? That E 4 pi r square is equal to what? 0. Equation 1, 0, flux equal to 0. So you can write that E equal to 0. So what conclusion we are getting? The conclusion we are getting that for a uniformly charged spherical cell, what conclusion we are getting? For a
For a
uniformly
uniformly charged spherical cell. Sir, I can't hear you.
what?
I can't hear you. Sir, I can't hear you.
Can you hear now?
Yes, sir, now I can hear.
What is the conclusion from this discussion? That the field outside and field inside the cell, field outside and field inside the cell. So what is the conclusion? The conclusion is that the electric field, the conclusion, what is the conclusion? The
Electric field.
field outside a spherical cell, electric field outside a spherical cell. Suppose this is a spherical cell which is charged. Charged. Charges are there over the surface of this. Okay. So charge sphere. So if you will go outside at any point, let's say r distance, so the electric field will be there and the magnitude is this one. This one. Now, and if this is a charged spherical cell like a football, and over the surface of the football, the charges are there over the surface of the football. Now, if you go inside the football, inside at any point, the field will be 0. This one is the proof. So inside the charge sphere, the field will be 0. Okay. So now so these are the two conclusions we are getting, that for a charged spherical cell like a football or any object, if the surface is charged, then if we'll go outside the cell, then the field will be field, and if we'll go inside that object, then the field will be 0. One more question comes, or MCQ type question also comes, right? That what is the field inside the spherical cell? It's 0. What is the field outside the spherical cell? The numerical may come. So using this formula, you can find out the field outside the spherical cell, charged spherical cell, right? So
Yes,
this
sir.
is these three are the applications of these three are the applications of Gauss law. Now we'll discuss dipole. Just briefly we'll introduce dipole, and we'll discuss dipole in the next class. Okay. So what is a dipole? Dipole, basically di means two. Electric dipole. Electric dipole. And for board exam, this question is very important, and for JEE NEET entrance examination also, the formula is very important. The question comes from dipole. Electric dipole. Okay. Electric dipole. Electric dipole means it will have two poles. It will have two poles. Two poles means one positive, one negative. One positive and one negative charge. Okay. One positive and one one positive and one negative charge, they will make dipole. Let's say plus Q and minus Q. Plus Q and minus Q, they will make a dipole, and let's say they are separated by a small distance 2a. 2a is the distance we are taking. Maybe it may be you can say very in micrometer or less than millimeter, very small distance between the two charges, then they form a dipole. Generally, they form due to the electron affinity or electron negativity, like that. Suppose some other atom, they pull them, and the electron cloud and the proton, the nucleus, they get separated, and a very small distance between the electron cloud and the nucleus, um, the separation becomes very small, so that they form a dipole. Because you know that the electrons revolve around the nucleus, right? The electrons revolve
Yes,
around
sir.
the nucleus, is positively charged. So if another atom which is positively charged, if it will come to the atom, these electrons will get attracted and they will accumulated at one place, right? They will accumulate it to one place, and the proton will be pushed and will be shifted, and a little bit distance will be created, that this 2a, let's say, and they will form a dipole. So they will form like this. This is, let's say, nucleus. It will have plus q, and these will be electrons, which will be minus q, and a small distance each 2a. This forms a dipole. This forms a
Hmm.
dipole.
Yes, sir.
Okay. So this is your electric dipole. So in electric dipole, we'll discuss two cases. And these two cases are very important for the board exam and also other competitive exams like NEET and JEE. In NEET and JEE, MCQ type question will come and board theoretical question will come. So electric dipole,
Hmm.
two cases. What are the two cases we'll derive? The two cases we'll discuss. One is the electric field will find out. Electric field electric field electric dipole. So we will find the electric field on the axis of the dipole. On the axis means these are the two charges, let's say plus q minus q, separated by a distance 2a. So this is the axis of the dipole. So any point, let's say P, we'll find out what is the electric field on any point on the axis. This is called axial case. Or we'll find the first case, that is the electric field on the points on the axis of the dipole, on the axis of the dipole. Okay, on the axis of the dipole. Now the second case that we will discuss, so two cases comes, either axial case will come for dipole or equatorial case will come for the dipole. Either axial or equatorial. Okay, either axial or equatorial.
Okay.
So equatorial case is what? Axial case is on the axis. We are supposed to find out the electric field at a point on the axis. And equatorial case is, suppose this is your plus q and minus q, two charges are there, and the distance between them is, let's say, 2a. Equatorial is the perpendicular bisector. You have to bisect it. So this is the perpendicular bisector, and at any point on the perpendicular bisector, you are supposed to find out the electric field. Okay, so going from plus q, let's say the field direction will be this direction, E plus q, and minus q will be towards. So this will be E minus q direction, and we'll find out their net field at a point P, which is on the equatorial. Equatorial means the perpendicular bisector. Equatorial means the perpendicular bisector. Okay. Equatorial means the perpendicular bisector. So two cases, one is electric field on the axis of the dipole, and the second one is electric field on the equatorial plane. Electric field at points on the equatorial plane. Equatorial plane means what? Perpendicular bisector. Equatorial plane means what? Perpendicular bisector. So 5 minutes just will discuss the axial case. In the next class, we will discuss the equatorial case. So you try to go through the NCERT book and derive it. Okay, derive it, and then we'll discuss the next class the equatorial case. So the first one is on the axis, point on the axis of the dipole. Points on the axis of the dipole. Point on the axis of the points on the axis of the dipole. Point on the axis of the dipole. So this is a dipole plus q and minus q separated by a distance 2a. Now this is the axis of the dipole, and you want to find out, let's say at a point P, the electric field. Now due to this plus q charge, what will be the direction of electric field? Due to the plus q charge, what will be the direction of electric field? To the left or to the right? Due to the plus charge, what will be the direction of the electric field?
Sir, to the right.
Plus charge, I'm saying. Plus charge will be, field will be
plus left.
Plus charge, the electric field will be to the left, E plus Q.
Yeah.
And due to this minus charge, the field will be towards. So for at point P also, it will be towards the minus Q. So we'll write this is E minus Q. As both the vectors are in opposite direction, so we'll subtract them. As both the vectors are in opposite direction, we'll subtract them. Okay, we'll subtract them. So E plus Q and E minus Q will subtract. E plus Q and E minus Q will subtract. Okay. So E plus Q and E minus Q. Okay. So what is the value? So total electric field E net at point P. Okay, at point P, E net equal to what? Now E plus Q, E minus Q is opposite direction. So E plus Q and E minus Q. So what will be the value? E plus Q is what? KQ by R square. KQ by electric field definition is KQ by R square. It will be KQ by R square. So what is R? Now from the center, the total distance between Q plus Q to minus Q is 2A. So if I'll take a center, so this will be half of AA. And from the center to the point P, we will take a distance, let's say R.
Yes, sir.
So what will be the distance from plus Q to P? Will it be A R minus A?
Yeah.
Diagram. A is the distance plus Q to minus Q, 2A. Midpoint is center O. So from O to plus Q, it's A. O to minus Q, it's A. Now from O to P, the distance is R. Now what will be the distance from P to plus Q? Now P to plus Q, R minus A, this distance. Okay, this distance will be R minus A. So KQ R minus A whole square, KQ by R square, KQ by R square minus E minus Q. E minus Q is what? A minus Q, this is minus Q. So what is the distance from P to minus Q? This is the distance. So this much is
Yes,
R,
sir.
A. So total will be R plus A. So E minus Q will be KQ by R plus A whole square. Now what we'll do, just we'll do the simple mathematics. KQ common, 1 by R minus A whole square minus 1 by R plus A whole square. Okay. Now we'll take the LCM. E net equal to KQ. LCM will be R minus A whole square, R plus A whole square, and just to cancel R minus A, so it will be R plus, just we are adding to fractional addition. Okay, R plus A whole square minus R minus A whole square. Now if we want to simplify it further, so it will be KQ A plus B whole square multiplied by A minus B whole square. What we can write? A plus B into A minus B. That will be A square minus B square whole square. And in the numerator, A plus B whole square minus A minus B whole square. A plus B whole square minus A minus B whole square. What we can write? That one will be A plus B whole square is A square plus B square plus 2AB. A minus B whole square is A square plus B square minus 2AB. So minus is there, cancel out. And
yes,
you will
sir.
get 4AB. This is like A plus B whole square minus A minus B whole square. What is the result? Result is 4AB. How? A plus B whole square is what? A square plus B square plus 2AB minus, bracket start, A minus B whole square is what? A square plus B square minus 2AB. Yes or no? So if we simplify further, it's A square plus B square plus 2AB minus a square minus b square plus 2ab minus b minus a square cancel 2ab, it's 4ab. This is the proof now.
Hmm.
These are the things you know in class 8 and 9.
Yes,
Right.
sir.
So k cube by r square minus a square whole square, and in the numerator, what is there? 4ab. A is r, 4ra. Okay. So what we can write? We are getting this electric field E net KQ 4RA by R square A square whole square. R square minus A square whole square. Now R is very bigger than A. A is very small. So if A is very
Hmm.
R is bigger than A, so we can neglect A square. Very small number. Let's say R is 1000, A is 0.01. So if we add 1000 plus 0.01, it will be 1000 0.01. Very small change. So A square we can neglect. If we'll neglect, then we'll get KQ 4RA divided by R to the power square R to the power 4. This 4 R will cancel out. It will become Q. So what is the net electric field you are getting? E net you are getting K 4QA divided by R cube. This is the result. Or in vector form you want to write, you can write that the net field will be along the direction of dipole. Dipole direction is negative to positive. P cap we represent. So we'll write E net direction is K, also we can replace 1 by 4 pi epsilon naught 4QA R cube P cap.
Yes, sir.
The derivation for this is the derivation for points on the axis of the dipole. Just you note it down today. Okay, you note it down today, and I'll send you this slides.
Hmm. Okay.
And
Yes,
practice.
sir. Yes, sir.
Also solve few questions based upon that from NCERT. Try to complete all the
Hmm.
exercise. For that, we'll discuss the last part, that is equatorial case and dipole in an external electric field. These two cases we'll discuss in the next class, and
Okay.
then we'll test.
Hmm. Yes, sir.
Type also numerical type. Both the questions I'll send maybe 20-30 marks. So within 40
Okay.
minutes or 1 hour, you will complete it and you will send me the scan of your pages.
Okay,
Okay,
sir.
PDF form.
Hmm.
Okay, so then stop it. But you could just go through it. Okay, don't waste the
Yes, sir.
time. Whatever we discuss, try to read it once and write it once also.
Okay. Okay, sir.